Hi folks, today we're going to talk about something called the discriminant. So you know how sometimes you have to, in the process of learning about something, you have to take a break and go learn about something else so that you can keep learning about what you were originally studying? That's kind of what we did with the radicals. So we took kind of a break from our conversations about quadratics and solving quadratics by factoring and stuff like that. We took a break from solving and finding solutions, and we did some radical stuff and simplifying radical stuff. The reason that we did that is so that we could then talk about things like the discriminant and the quadratic formula, which you might remember from last year. So the essential question today is, how do we find the discriminant? And the second essential question is, what does it tell us about the number of solutions for our quadratic? Okay, so first of all, we are talking about quadratics. Remember that on a graph, and this is not something you need to draw, but just on a graph, we talked about solutions for a quadratic. And the synonyms for solution were root and 0 and x-intercept. So we could either have two solutions, or we could have one solution, or we could have no solutions for our quadratic. And so today we're going to be able to tell the number of solutions based on the discriminant. The discriminant is b squared minus 4ac. And one of two things may be running through your head right now. One of them might be, what in the world are a, b, and c, and where do they come from? Well, they come from standard form of a quadratic. So ax squared plus bx plus c. So that's where they come from. And then some of you might be thinking, oh, well, I recognize that. That's part of the quadratic formula. And I realize that I'm kind of writing all over my notes right now. But I do want to mention the quadratic formula, which was x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. This is a formula that's been on your formula chart since Algebra 1. It helps you find the solutions for your quadratic. Sometimes it gives you two answers, sometimes it gives you one, sometimes it doesn't give you any. So the discriminant is this thing that's underneath the radical. Now we took a break from finding solutions to quadratics so that we could talk about simplifying radicals and imaginary numbers and things that happen when the radicand is negative. So that's going to help us with our discriminant learning and applying the discriminant. So the discriminant, b squared minus 4ac, it indicates the nature of the roots. So let's identify the discriminant and then describe the nature of the roots. We have 4 examples and a summary. So these notes are not incredibly long. But I notice that if I'm going to identify the discriminant and describe the nature of the roots, and I have to pick out a and b and c in order to do that, my quadratic better be in standard form in order to pick out a, b, and c. And this is not. Why is this not standard form? Because the 3 is over here, and this equation should equal 0. So I need to move this 3 back over to the left side with everything else. So 2x squared minus 5x minus 3 equals 0. So my a is 2. My b is negative 5. My c is negative 3. My discriminant that tells the nature of the roots is b squared minus 4ac. Well, b squared would be negative 5 squared minus 4 times a, which is 2, times c, which is negative 3. Now, if you type this into the calculator, so be it, that's fine. But if you do it without a calculator, negative 5 squared is 25. Negative 4 times 2 is negative 8, and negative 8 times negative 3 is positive 24. So that's 49. So my discriminant, b squared minus 4ac, is 49. Well, remember that the discriminant is what is underneath the radical here. And whenever you use the quadratic formula, you do negative b plus the square root of this over 2a, and then you do negative b minus the square root of this over 2a. So if your discriminant is 49, the square root of 49 is 7. It's a nice, pretty number. And so you're going to get two different solutions, one when you add 7 and one when you subtract 7. So the nature of our roots is that we have two real, not complex or imaginary, there's no negative under the radical, so we have two real rational roots. Rational means they can be written as a fraction. So this means no I, and this means fraction or integer. So because 49 is a perfect square, then we have two real rational roots. So that would look like this. So let's move on to number 2. Is that in standard form? No, it's not. Should I move the x squared to the right or these two to the left? Well, I want my leading coefficient of x squared to be positive, so I'm going to move these two things over there. I have x squared minus 6x minus 20 equals 0. That's standard form. My a is 1, my b is negative 6, and the c is negative 20. I need to calculate the discriminant, so b squared minus 4ac. Go ahead and take a moment to substitute your values of a, b, and c into the discriminant formula and find your discriminant. Write it on your line down here. So pause your video and try to finish. All right. You'll see I made a mistake whenever I was adding. But my discriminant is 116. So if I were to take the square root of 116, that is not a nice, pretty number. So even though I still get two real roots, like I'm not taking the square root of a negative number, so it's not imaginary, it's going to be real, my answer is going to have some kind of, like if I were typing it in a calculator, it'd have some kind of like never-ending decimal. So that means that it can't be written as a perfect fraction, so it's two real irrational roots. Okay. Remember that the discriminant is what is under the radical in the quadratic formula. Let me see if I can fix that a little bit. There we go. That looks a little better. So is this in standard form? No. So I want you to pause your video. I want you to, number 1, get this in standard form. So this needs to equal 0. Number 2, I need to get a and b and c values. And then number 3, I need to substitute those values into my discriminant formula. So I want you to do that. Get your standard form, pick out a, b, and c, and substitute those values into your formula. Pause your video and try it out. So what happens? Your discriminant ends up being 0. Well, what happens when you take the square root of 0? Yeah, it's a perfect square. You get 0. But if your quadratic formula has negative b plus or minus 0 over 2a, well, when you add 0 and subtract 0, it's not different. If you add nothing or subtract nothing, you still get the same thing. It doesn't change. So that means that instead of there being 2 answers, there's actually only going to be 1 answer here, because this part goes away. And what you're left with is one real number for your root. So if the discriminant is 0, then you only have one real root. because the square root of 0 is 0, and if you add 0 or subtract 0, you don't get any different numbers. So let's move on to our last example. Is it in standard form? You bet. A, B, C. Go ahead and fill them in. A is negative 2, B is 4, C is negative 6. My discriminant is b squared minus 4ac when I substitute my values. I have 4 squared minus 4 times negative 2 times negative 6. By the way, I didn't put parentheses around this, not because of any other reason except it's not absolutely necessary. The 4 wasn't negative, but I could put them around it if I wanted to. So 4 squared is 16. Negative 4 times negative 2 is 8. 8 times negative 6 is negative 48. And if I subtract, I'm going to get a negative 32. So that's my discriminant. Well, folks, what happens when you take the square root of negative 32? Yeah, it gets broken up into the square root of negative 1, the square root of 16, and the square root of 2. That's 4i square roots of 2. So I'm going to end up with negative b plus this over 2a and negative b minus this over 2a. So I'm going to have two answers, but they're going to be complex roots, also called imaginary. Remember our conversations about I and how it's the square root of negative 1? That's what happens when you square a negative number? Well, that's what happens. You have two complex roots here, and it shows up kind of like this. That's what it shows up as really having no solutions, because you can't graph complex numbers on the x and y axis. So let's summarize what we learned today. So if the discriminant, b squared minus 4ac, if it's greater than 0, maybe an example is 49. If it's greater than 0, and meaning it's positive, and it's a perfect square, so 49 is a perfect square, then what was the nature of the roots? Well, when the discriminant was 49, the nature of the roots was that we had two real rational roots. So we had two real rational roots. And on a graph, how many times does it intersect the x-axis? Well, roots are the x-intercept, so it does it 2 times. So twice. Next example. If the value of the discriminant again is positive, an example would be 116, and let's say that it's not a perfect square, so no, 116 is not a perfect square. Well, what was the nature of the roots? Well, when the discriminant was 116 and it was not a perfect square, we still had two real roots, but they were irrational because the square root of 16 wasn't a perfect square. So two real irrational roots. And still, there are two x-intercepts. They're just crossing at places that are not nice and pretty. What about if our discriminant is less than 0, if it's negative? When our discriminant was negative, that was our last example, we had two solutions, but we had to take out the square root of negative 1, which made it complex. So we have not a perfect square, and even if it were, it wouldn't matter, because we have two complex roots. And it never intersects the x-axis. Remember how we talked about how that looked like it didn't touch the x-axis? And then finally, what happens when your discriminant is equal to 0? Well, yes, 0 is a perfect square. However, when you add 0 or subtract 0, that doesn't change anything, so you're only left with one real root. One real root. and it only crosses the x-axis once. And what that looks like is maybe an intersection at the vertex. So that's the discriminant. That's how we figure out the nature of our roots.